Do we submit the work?
Okay, so far we've been talking about molecular polarity or the whole molecule. I want to talk to you about bond polarity. So if I were to zoom in to just one bond in the molecule, so if I were to have a, let's go with an easy one that we've done a bunch. If I were to have CCl4, okay? This molecule is non-polar, but if I were to zoom in to just one of the bonds and I were to look at just this one bond, I have to ask myself, is that bond polar or is that bond non-polar? And this has to do with how even they share electrons, which is what I'm going to talk about right now, which is not molecular polarity, but bond polarity. And the way that I want to bring up bond polarity is to remind you of hydrogen bonding, okay? Hydrogen bonding is a third type of intermolecular attraction. So we have dispersion forces, everything has that. Dipole-dipole, which only happens in polar molecules. And then we have a very precise type of bonding called hydrogen bonding. And this is a strong type of dipole-dipole. It's a strong dipole that happens when hydrogen bonds to F, fluorine, O, oxygen, or N, nitrogen. And I like to say it's when hydrogen just wants to have fun. Okay, so when hydrogen bonds to F, O, or N, we can get hydrogen bonding. And the reason for this is that N, O, and F have such high electronegativity that they pull the hydrogen's electrons away, leaving its proton exposed. It's a really, really strong intermolecular attraction, but it's important to remember that it's still weaker than an actual covalent bond. In fact, I hate that they call it hydrogen bonding. It really irritates me that they call it hydrogen bonding. I wish they called it hydrogen forces or something. Now, this TED-Ed is the one that we already watched. And I want to just show you a little piece of this. All right. Here we go. I want you to watch, to kind of rewatch this part, because this is what makes hydrogen bonding so special.
The oxygen atom and two hydrogen atoms within a single water molecule is like a tug of war between a big, strong football player and a cute little toddler. Oxygen is a larger atom with more protons in its nucleus than hydrogen. These positive charges are like a person's physical strength. They are able to attract the negatively charged electrons in the bond, just like a strong individual is able to overpower a weaker individual in a tug of war. So, oxygen is able to attract more than its fair share of electrons. Because hydrogen is smaller and has less strength, or fewer protons, it loses the tug of war and attracts fewer than its fair share of electrons. So the oxygen in water behaves as though it's negative, and the hydrogens behave as though they're positive. The bonds within a single water molecule are called polar covalent bonds. Covalent means
Okay, so there we go. We've got these polar covalent bonds, and this is caused because you have oxygen, which is this big, strong football player like molecule. And in the end, it makes the whole molecule become polar because of this hydrogen bonding. All right. This is all because of something called electronegativity. Now, this is something that we talked about already. We already talked about electronegativity, and you can tell because I already showed you this terrible chart that has bromine mismarked, and it gives you a relative value of the strength of all of the atoms. This is how strong the atoms are and how much they would win in a tug of war between electrons. So a couple of things I want to point out to you. Hydrogen, as far as non-metals go, it's here and it's here, is pretty weak. It's pretty weak compared to other non-metals. All right. Oxygen, there it is, pretty strong compared to other non-metals. Fluorine, even stronger. And then you've got all the metals. The metals have really, really low electronegativities, which means they don't pull on electrons at all, which is why we're going to see the different types of bonds form. So if you look at electronegativity, and This entire analogy today is based off of penguins and polar bears. You can see that the polar bears, the ones with the stronger, bigger electronegativity, live up in the northeast side of the periodic table, and the penguins live kind of down in the southwest side. This is just to say that the polar bears have very strong electronegativities, which means that they are tugging on those electrons even more. So it turns out that most bonds, even though we've said you've got ionic bonds and covalent bonds, it turns out that most bonds are kind of ionic covalent-ish. There's some kind of gray area here that happens between ionic and covalent, and we get something called polar covalent and non-polar covalent, which I'll tell you about more today. And it's that difference in electronegativity that's going to determine these different bond types. So again, electronegativity by definition is just an attraction an atom has for a shared pair of electrons. If in the bond you have a more electronegative atom, it's going to become a little bit negative. Now this example has hydrogen on one side and chlorine on the other side. And the chlorine pulls the electrons towards it, so the chlorine becomes a little bit negative. It's stronger. It's a polar bear. The hydrogen doesn't have as much strength, so it becomes positive because it's losing those electrons, and electrons are negative. This is delta minus and delta plus. This just means a little bit negative and a little bit positive. So if we look at HCl and we think about it like polar bears and penguins, the bonded pair of electrons spends more time around the more electronegative atom or the polar bear. So chlorine becomes more negative, right? And that symbol a little bit negative is just so you don't get confused with actual positive and negative charges. So we can also have an instance where things are shared evenly. All right, you can have a true covalent bond. It's when electrons are shared perfectly evenly, and there is an even sharing, which creates an equal symmetrical electron density. This usually happens in identical atoms. So think things like O2, right? That's one we've looked at several times. When oxygen bonds to oxygen, they're both oxygen, so they're going to pull evenly. Another place that non-polar covalent bonds happen that I told you about just today is here in C's and H's. Okay, when you see C's and H's, you think non-polar, no matter what, and that's just because they're very similar in electronegativity. They're almost identical atoms. So when you think about that cloud of electrons, the cloud of electrons is shared evenly between the two. All right, back to my polar bears and my penguins. It's like a polar bear and a polar bear and a penguin and a penguin. They're going to have equal attracting strength, and this is what creates non-polar bonds. Okay, the polar bonds, again, the electrons are shared unequally. We have asymmetrical electron density, and it results in a partial charge. And those partial charges we call dipoles. That word dipole just means a charge. You can have a charge within a bond, or you can have a charge, a dipole, on an entire molecule. If you've only got two atoms, the bond polarity is the molecular polarity. So that's why all these little examples I'm showing you just have two atoms, because I'm just talking about one at a time. And the reason they often draw them as like big over on this side and smaller over on this side is because, again, there's more electrons hanging out around the more electronegative atom. So penguins and polar bears, the ice cream is the electrons. The electrons spend more time around the polar bear or the more electronegative atom. All right, creates this partial charge. So here's the thing. Electronegativity differences can be a little or they can be a lot. So if you have an atom that has an electronegativity difference that's so incredibly much higher than what it's bonded with, sometimes it pulls the electrons so hard, it plucks the electrons away, right? And that's what makes an ionic bond. An ionic bond, which we've learned so far as when they transfer electrons, that's why they transfer electrons, because they pull so hard that they're actually pulling the electrons away. And then you get left with not a positive side and a negative side, but you literally get left with a positive ion and a negative ion. Okay. So we've got non-polar, and this is non-polar covalent, polar covalent, and then ionic, right? Sharing equally, sharing unequally, and sharing so unequally that you've ripped it away and now you're not even sharing anymore. Okay? Penguins, polar bears, sharing equally, sharing unequally, and sharing so much that you've ripped the ice cream away. And once you've ripped it away, you create the charges, which then draws, ironically, in the polar bear and the penguin, will then make them stick together. That's where the analogy breaks down a bit there, I suppose. Okay. So that's bond polarity. The thing is, again, I'm zooming in. I'm just looking at one single bond. There's some numbers that you can remember, okay? In general, a bond is considered polar if the difference in electronegativity is above 0.3 or more. I like to think about it as more than hydrogen and carbon, okay? Hydrogen and carbon is non-polar, no matter what. So if there's a greater difference than hydrogen and carbon, then it's going to be polar. If it's less than hydrogen and carbon, it's non-polar. That's the easiest way that you can think about it. All right. So we've got non-polar, polar, and then if it's anything more than 1.7, it just becomes straight up ionic. So you can look at this chart again, right? Here's this chart. It's showing you this. It's saying if they're real close, if they're the same thing, or if they're carbon and hydrogen, they're non-polar covalent. If there is a difference from about here to here, and again, it's a gradient, this is a little bit of gray area, then we call it polar covalent, and up here is more the ionic area. And you'll see here it says percentage of ionic character, because again, in chemistry, it's not just black and white. There are things that are, so on the borderline that they act a little ionic and a little covalent. But luckily, I've given you pretty good examples, like Cl2, right? Cl2 is going to be a Cl bonded to a Cl. They're the same thing. So Cl2 is going to be non-polar because, again, they're the same thing. The difference in their electronegativity is exactly the same. The next one is HCl. So I've got H bonded to Cl. What I need to do is I actually need to go to that chart. And I gotta go find that chart. Ooh, it's way back. The chart is way back. It's so far back that I'm gonna forget what I'm looking at here. Okay, so I've got H and Cl, 2.2 or 3.16. So that chart is what I use to determine the bond type. And on your notes, I put that chart somewhere easy to find so you didn't have to go looking for it very much. Okay, sorry that I wrote over it, but it's 3.16 minus 2.2. That's chlorine, 3.16 minus 2.2. It has a 0.96 difference. What that means is it falls somewhere in here, so it's considered polar covalent. The last one is NaCl. Feel like it's like spoiler alert. If you don't know that NaCl is ionic, then you probably have been sleeping through all of Chem 1. But you could determine that by looking at the chart. You could find Na on the chart, you could find Cl on the chart, and you could subtract those and get 2.23. and that would turn out to be an ionic bond. All right. Here's where it gets interesting, right? Because I am not always just looking at bonds. Most of the time I'm looking at molecules, right? So it says, determine if these molecules contain polar bonds. Now, before I even start, I'm not talking about the polarity of the molecules. I'm talking about the polarity of the bonds within the molecules. So this very first one is NCl3, all right, C2H6, H2O, and CH2F2. All right, so in order to find out the bond polarity, you have to go to your chart. So NCl3, you find nitrogen on the chart, 3.04. Cl3, you do not have to do any, like, I've seen kids do weird things where they like multiply it before they subtract it. You just say 3.16 is chlorine minus 3.04 is nitrogen, and that equals 0.12. So is that polar or non-polar? It turns out that that's below the 0.3 threshold. So that's actually non-polar, which is interesting. I gave that one on purpose because those are 3 non-polar bonds, but these lone pairs up there make that a polar molecule. Ooh, mind blown. 3 non-polar bonds, but the lone pairs make the whole molecule polar, which again makes some interesting things happen in chemistry. Now, C2H6, I've told you over and over and over again, C's and H's are non-polar. So I hope you don't have to look it up. But if you did have to look it up, you could look it up and you could see that your H and your C, my poster child for non-polar, are close enough together. So that 0.35 difference, I know it's greater than 0.3, which is what that one chart said, but I could kill that chart for saying that. It's non-polar. Now H2O, oof, you got the girl Nancy talking about the polar molecules. It's really polar. It's incredibly polar. It's so polar that it creates hydrogen bonding, right? So the hydrogen has that 2.2 and the oxygen has 3.44. So 3.44 minus 2.2 equals an electronegativity difference of 1.24. That's a very polar bond. And it's got lone pairs, so it's a polar molecule. So they're really polar bonds and a really polar molecule, which makes it really, really, really polar, which is why we get that really strong type of bonding called hydrogen bonding. Now the last one, CH2F2, you can see there that it has non-polar bonds with the C's and the H's. That's fine. We know these are non-polar. We've talked about it before. That's that 0.35. But then if you were to do the math on the C's and the F's, the C would have the 2.55 and the F has the 3.98, which gives it a difference of 1.43. So it has 2 polar bonds and 2 non-polar bonds. And guess what? The whole molecule is non-polar, right? So there's a lot more to polarity that can kind of tend to confuse you. So polar bonds make dipoles. The word dipole, I hate the word dipole, but the word dipole can refer to the polarity of an individual bond, the net polarity of a whole molecule, or I've even heard them use the word dipole to call a polar molecule a dipole, like call a water molecule a dipole, which I think is a weird phrase. But if you just remember that dipoles mean charges and you work your way through all of this, you'll be okay. The other thing I want to show you is that sometimes there's a notation where they draw an arrow. This is an arrow, and they point the arrow towards the more electronegative atom. So they show that that atom is pulling electrons towards it, which makes it more negative. And when it does that, it leaves the hydrogen to become positive. And then I kind of made a point of this all the way, but don't forget that molecular polarity is not bond polarity. Molecular polarity is different than bond polarity. So non-polar molecules can contain polar bonds, and polar molecules can contain non-polar bonds. And if a molecule has all non-polar bonds, it's automatically a non-polar molecule, like hydrocarbons. And this is where my organic chemistry teacher comes in. This is non-polar. That's CH4, it's butane. I promise you it's non-polar in every way, shape, and form. And if you're wondering about, that one that we did before, I'll tell you about gray area in a second. The reason that this is, and this is what I was talking about earlier with Sally, the polar bonds in a molecule can cancel out, right? So this is what's going on here. You might have 3 polar bonds, but it's symmetry, right? It's all about symmetry, so they cancel out. So the shapes that, again, have potential to have non-polar shapes are linear, tetrahedral, and trigonal planar. And that's because there's no central atom that has there's no bonds on that central atom. And this is my gray area. If you care, there is a little bit of gray area, and I showed you this molecule before. NCl are only very slightly polar, and sometimes they'll even call NCl nonpolar because it's comprised of all nonpolar bonds. I see NCl as a polar molecule because of the central atom having the lone pairs. But I just want to warn you, if somebody says to you, oh, hey, it's nonpolar because it contains all nonpolar bonds, don't say I didn't tell you, because like I said, it's a little bit of gray area. I promise on tests, I won't give you any gray area questions. I give you very much not gray area. Okay?